Hello there. So this is the third video of section 3.2. So here what I want to do is give a slightly more concrete example of theorem 5. What we're going to do is we're going to calculate the determinant of A and its transpose. We won't do the whole thing. I think you only need the first step of this process to really see why theorem 5, which again states that the determinant of a matrix A is equal to the determinant of its transpose, of course assuming the matrix has a determinant, so assuming it's a square matrix. And then I want to actually prove theorem 6. I think the proof of theorem 6 gives us some really cool insight as to like why these things are true and sort of how to work with specifically determinants and how to work with these matrices and how to prove things. So without further ado, we've got this matrix A. So from left to right, 1, negative 3, 6, 0, 5, negative 2, 4, negative 1, 8. So first things first, let us calculate its transpose. So what you do, I always get this rotation mixed up, but you rotate it like that. I think thinking of it as a rotation is maybe not the optimal way to do it. I just like to basically go down the columns and rewrite them as rows. But anyways, there is a transpose. And so what we're going to do is we're going to calculate A by expanding across, or down, I guess, the first column of A. And then we'll calculate the determinant of A transpose by expanding across the first row. And so one thing you might already notice, well, the first column of A is equal to the first row of A transpose. And so this is going to prove to be very useful in doing this. Hopefully I get this right. I think I've calculated this correctly. Plus 4 times the determinant of negative 3, 6, 5, negative 2. So I don't need to go further than this because I think just writing out the determinant of A transpose will give us sort of a good idea of what's going on here. Let me double check with my notes that I got that correct. Yes, okay, that's good. All right, so now if we expand across the first row of A transpose, well, I'm going to get 1 times determinant of 5, negative 1, negative 2, 8, minus 0 times the determinant of 3, negative 1, 6, 8, plus 4 times the determinant of negative 3, 5, 6, negative 2. And so notice these expressions aren't exactly the same. Specifically, each of these 2 by 2 determinants are slightly different, but I claim that the values of each of these determinants are the same because notice for this first matrix, the value of the determinant is 5 times 8 minus negative 2 times negative 1. Right, so that's this first one. The second one is, well, 5 times 8 minus negative 1 times negative 2. And so while the matrices are different, the determinants are the same because the only thing we're switching about these matrices is the order that these non-diagonal entries appear in. And because of that, their determinants will be the same. So in fact, each of these terms is the same, and so these expressions are equal. And so that's sort of, I think, gives a better picture as to why this theorem is true without necessarily proving it in full, is basically that the way we switch everything around in this way sort of preserves how this cofactor expansion will work. So that's theorem 5. Let's move on to theorem 6. So before we get into the proof of theorem 6, what I want to do is look at a few elementary matrices because I want to study something very specific about their determinants. So we'll state theorem 6. or a slightly abbreviated version, the important part of theorem 6, that determinant of A times B is equal to the determinant of A times the determinant of B. So this is what we're trying to prove. All right. So I'm going to look at 3 elementary matrices. 1, -2, 0, 0, 1, 0, 0, 0, 1. E2, which is equal to 0, 1, 0, 1, 0, 0, 0, 0, 1. And E3, which is that matrix. So again, this corresponds to -2 row 1 plus R2. This corresponds to the row swap of R1 and R2. And this corresponds to R3 times 3. All right, so why do I have 3 elementary matrices on the board? Well, remember that, again, as I just stated, that each of these matrices corresponds to a row operation performed on a matrix A. And remember, by multiplying by these matrices on the left, we can, in a sense, perform that row operation on the same matrix. So remember, if I were to do these 3 row operations in order, the matrix I would get would be equivalent if I had just multiplied A on the left by these 3 matrices in order. And remember, I think in video 1 of this very section, we showed how row operations affect a matrix, right? So specifically, this row operation of 2 row 1, -2 row 1 plus row 2, right? This didn't change the determinant at all. Okay. Well, notice that the determinant of E1, well, E1 is a lower triangular matrix, and therefore its determinant is just the product of its diagonal entries is equal to 1. So keep that in mind. So remember, this corresponds to the row operation of row 1 swapped with row 2. And this one would take a little more work, but if you expand it across the 3rd row, you could actually get that the determinant of E2 is equal to -1. And remember, this row operation of swapping row 1 with row 2 tells us, in relating determinants to row operations, to multiply the determinant by -1. Well, remember, this one is 3 row 3, and sure enough, the determinant of E3 is equal to 3. So you might already sort of notice a small trend here, that the determinants of these elementary matrices, in a way, correspond to how their respective row operation affects the determinant of a matrix. So to see that in a little more concrete detail, I actually want to row reduce the following matrix. Which we'll call A. Let's do it this way. Well, I want to row reduce this matrix. And using these row operations, look at the determinant at the beginning and the end, and then show basically that this multiplicative property is always going to hold with these elementary matrices. And what we're going to do with that is use this fact in our proof to show that the multiplicative property will hold with all matrices. So if I were to row reduce this matrix using these 3 row operations in order, so I do -2 R1 plus R2, Then I'm going to swap row 1 and row 2. And then I'm going to multiply 3 times row 3. And so, almost too conveniently, this matrix row reduces to the identity matrix. All right, well, so we now know how to work backwards in order to find the determinant of this matrix, right? So we know that the determinant of this matrix is equal to 1. Well, since I multiplied by 3 here, I should divide by 1/3. And so the determinant of this matrix is equal to 1/3. Since I swapped rows here, I need to multiply by -1. And so the determinant of this matrix is equal to -1/3. And since this row operation was just a row replacement, well, I don't actually have to change anything about the determinant. And so the determinant of my original matrix is -1/3. And so if I let this matrix be A, then notice I calculated the determinant of A by sort of multiplying by the reciprocals in a sense of all of these. But so notice in particular, and this is the very important fact to notice from this example, that the determinant of A times the determinant of E1, or actually, we should do it in this way. So the determinant of E3 times the determinant of E2 times the determinant of E1 times the determinant of A is equal to the determinant of I sub n. And notice that since these were the 3 matrices I used to row reduce A, this shows that these 3 elementary matrices, and sort of my purpose with this motivating example is to argue that this type of property is always going to hold with elementary matrices, that this sort of multiplicative property holds with these elementary matrices because they correspond to these row operations, which we've already shown sort of exhibit this multiplicative property. So what to note here is that if I can get to the identity matrix specifically, or any matrix really, using a sequence of row operations, then this fact is true. That is the product of each of the individual determinants of the elementary matrices corresponding to row operations times the determinant of A is equal to the determinant of In. So using this fact, I want to now give a brief proof of theorem 6. All right, so right off the bat, I'm going to have to make one assumption that we haven't technically proved yet, but I think is a reasonable assumption to make. So this is a fact we haven't proven yet, but it is true. So if A is not invertible, then A times B is not invertible. So that is if I have 2 matrices A and B, and one of them is not invertible, then their product is not invertible. And so this actually, in the case where one of these 2 matrices is not invertible, immediately implies the result, because since A is not invertible, its determinant is 0, as we've already shown. Well, so anything times 0 is equal to 0. But since AB is also not invertible, its determinant is equal to 0. And so in the case that at least one of the two matrices is not invertible, we're good. And so notice here that we could have done this exact same thing assuming B was not invertible. So this covers the case where at least one of the matrices is not invertible. So this means we can assume that both A and B are invertible. But in fact, we really, I guess, only need to use the fact that A is invertible. But so since A is invertible, remember by the invertible matrix theorem, which I'll abbreviate as INVMAT-THM, remember A row reduces to the identity matrix. Well, and so we're going to write this in a slightly different format because what I'm writing is technically not the set of row reduction steps that reduces A to the identity matrix. But remember, each of these elementary matrices is invertible. So I could just move this product of elementary matrices over, which would give me a product of elementary matrices, which would row reduce A to the identity matrix. So A being invertible and row reducing to the identity does in fact imply this fact here. But so this means that the determinant of A times B, which sort of using our determinant notation will abbreviate like this. Well, what I can do is I can just replace A by this product of elementary matrices, right? Because I've already shown that A is equal to this product, and I can just drop the IN because it doesn't change anything. Well, now is where we call on sort of the idea from our example, right? That the determinant of this product, where this is just a row reduction of B, well, since these are elementary matrices, I can just bring them out and multiply by each individual determinant. And so this is why I wanted to show the example, was for this step in the proof, to argue that, at least to show an example of that we can do this. All right, because remember, each one of these is an elementary matrix corresponding to a row operation, and we showed that each individual determinant of the elementary matrix corresponds sort of to the same way that a row operation would affect a matrix. So I can pull these out, multiply by each of their individual determinants, and multiply by B. But since A is equal to this product is just equal to the determinant of A. And sure enough, this is equal to the determinant of A times the determinant of B. And so that proves maybe one of the coolest theorems we've seen so far in this class, that the determinant satisfies the multiplicative property. All right, so that finishes up section 3.2. We will next do section 3.3, which will be the last section before your midterm.